Hello everyone, I will introduce the first measurement of on-device training performance towards ubiquitous learning. It's science work advised by Professor Shangguang Wang and Mengwei Xu from Beijing University of Post and Telecommunications, and cooperate with Xipeng Wang Yuanqiang Liu from Peking University and Yunxin Liu from Tsinghua University. First, I will introduce the inspiration and the background of our measurement. As Moore's law says, we are witnessing the rapid growth of computing power of on-chip processors. For example, in 2010, Samsung released the Galaxy S, which has only 512 MB of random access memory, also called RAM. While in last year, the Galaxy Note 20 has 24 times more RAM with almost the same size with Galaxy S. In addition to the processor, the number of smartphones around the world is also growing rapidly. All of the above reveals that we can do more with our smartphones. Deep learning is one of the interesting and meaningful things that our smartphones can do, and many applications have used deep learning to realize some auto functions such as photo beauty, face detection, text auto-correct, sound recognition, etc. The number of related applications has increased about 30% in just 3 months, and the speed is still increasing. However, most of the applications only do the inference stage of deep learning on edge devices. Their training stage of deep learning is still commonly placed on data center for its tremendous demand of massive training data and computing resources, which means to enable deep learning, users must communicate with data centers to pull models or push their personal information to data center. This will undoubtedly increase the load of the data center and the possibility of personal data leakage. In recent years, however, we are witnessing the emergence of a new paradigm that directly leverages edge devices for model training, referred as ubiquitous learning. Use cases of ubiquitous learning abound, such as AI input method, virtual assistant, item recommendation, etc. Ubiquitous learning makes it unnecessary for smartphones to communicate with the data center. They can communicate with each other and complete the training stage of deep learning. The learning protocols might diversify. For example, federated learning, split learning, and local transfer learning. They all rely on a fundamental system component that is on-device training library. Given the high constrained resources on edge devices and the huge resource demand of deep learning training stage, it is intuitive to ask whether the edge device can really afford training modern models, and if so, do current libraries efficiently support that? Our measurement gives a system-level understanding of how ubiquitous learning is supported by commodity edge devices and the state-of-the-art training libraries. The training library is a mobile neural network, also can called MNN. It's a lightweight inference framework proposed by Alibaba in 2019. It is very easy to use and has versatility, which is reflected in the fact that it can support operations from TensorFlow, Caffe, and support common neural networks such as CNN, RNN, GNN. Most importantly, it has high performance in on-device training. As shown in the comparative experiment on the right table, TensorFlow and PyTorch can only try on Raspberry Pi instead of smartphones, and DL4J, another training library, supports training on smartphones. It performs worse than MNN, whatever in terms of training time or memory usage. For example, when we choose batch size 4, deep learning 4J will end in out of memory, while MNN can still do more. We carry out our experiment on 6 devices with different system on chip and computing capacity. As summarized in the left table, we test 5 classic classical CNN models in our experiments, including LearnNet, AlexNet, MobileNet, SqueezeNet, and GoogleNet. Detailed model parameters are shown in the right table. Okay, now I'm going to show our experiment results and our findings. First, let me show the overall latency of MNN. The picture illustrates the inference and training time of 5 chosen models. Our primary observation is that the training time is much larger than the inference time, maybe up to 70.8 times gap with MobileNet and the batch size 16. Such a measured gap is significantly larger than the theoretical flops gap, which says that training time should only be around 3 times of inference. The conflict between experimental results and the theory is because MNN was first released as an inference-only engine, and thus highly optimized for that. The training spot was first added in late 2019, and the implementation of many operators is to be improved. Furthermore, we measure the training time with different numbers of used CPU core. You can get the comparison by reading the head of the figure. NC means the number of CPU core. Our main observation is that multiple cores can often speed up the training as compared to one single core. However, it doesn't mean that more core will always bring improvements. In fact, distributing the training into all 8 CPU cores often leads to the highest training time, and 4 CPU cores achieves the lowest latency in most cases. This is mainly because mobile CPU cores are asymmetric. That is to say, big little architecture. Common smartphones are composed of 4 big CPU cores and 4 small CPU cores to adapt to various scenarios. The performance improvement of some CPU is masked by the additional switching overhead. Apart from overall and non-core diversity, we also observe that with larger batch size, the training time increases more significantly than the inference time. To answer this question, we dive deeply into the CPU usage during training and the inference stage. As confirmed in the shown picture, the CPU usage during training is already close to maximum with relatively small batch size. Please note that the maximum is 400% as 4 CPU cores are used by default. While during inference, using large batch size can noticeably increase the CPU usage. Thus, the inference latency increases sublinearly. Next, we compare the cross-device training performance. Overall, the performance disparity across devices is pervasive and can be up to 4 times gap. For collaborative learning across mobile devices like federated learning, such heterogeneous computing capacity needs to be considered to better synchronize the training pace. Interestingly, we also observe that different devices have distinct model affinity. For example, SqueezeNet trains faster on Meizu, while AlexNet trains faster on Huawei Mate 13. That's interesting because you can choose suitable devices for specific training tasks and get extra gain. We further break down the end-to-end training time into the lowest operator level. As shown below, raster and matrix multiply are the 2 most time-consuming operators. Raster operator is a unified implementation of all traditional operators that are related to tensor shape transformations, including slice, concat, reshape, broadcast, etc. For example, the convolution operation in MNN is implemented with 3 raster, 2 to convert input and filters, 1 to convert output, and 1 matrix multiply. MNN doesn't implement those operators individually is mainly because using one operator raster to represent those similar operations can help them focus on optimization. However, such a simplified design inevitably sacrifices the running performance of operators. Okay, next I will show you the memory footprint of MNN training stage. As observed with a typical batch size 16, the memory usage of the tested model is about a few GBs, except for LearnIt, because it only has 3,000 parameters. Noting that our experiments are carried out in a clean environment without other surrounding applications. In practice, however, requesting such a high amount of memory may cause other applications to be swapped out, or raises the risk of training application itself to be moved out of the memory by the OS. Therefore, the memory usage of on-device training tasks should be more strictly confined, indicating that an even smaller batch size can be eventually employed. Then we measure the energy consumption by running each model for 20 batches and subtract the energy consumption during that running period by the baseline energy when no training task is running. As observed, the per batch energy by energy consumption significantly increased with larger batch size, mainly because of the increased training time. However, the per sample energy consumption decreases with larger batch size. This is because the training time doesn't linearly scale with batch size, since the larger batch size benefits the intra-operator parallelism. And it indicates that to iterate over a local dataset using larger batch size can be more energy efficient. We then study how our system configurations affect the training performance. We vary the CPU core numbers and the frequency for each core. The result of experiments show that for training time, using 4 big cores with the highest frequency achieves the best performance. However, in consideration of energy consumption, using only 1 small core with the lowest CPU frequency leads to the lowest usage. Its energy consumption is only 43.7% of the optimal case of training time, despite it runs 28.9 times slower. The observation indicates a larger space of trade-off between training time and energy consumption. In reality, both metrics plays a key role in ubiquitous learning. Taking federated learning as an example, developers expect the on-device training to be completed shortly. Therefore, the global model converges fast. Meanwhile, the energy consumption should be minimized to not compromise user experience. Next, as we all know, to reach usable accuracy, often the training phase often takes a substantial period of time. For example, minutes for each round of federated learning, or even hours of continuous local transfer learning. Such a local duration of intensive computation may lead to thermal issues, and therefore the CPU frequency change even without any other application running. Thus, we investigate into the thermal dynamics and their impacts on the CPU frequency. On both tested devices, we observe the temperature rising and the CPU underclocking. When the frequency drops to the threshold, the temperature will be stable, though the specific behavior differs on different devices. For instance, Meizu takes less time to the peak temperature, and both devices' peak temperature is different, which is preset by the manufacturer. Such heterogeneous thermodynamics may complicate the ubiquitous learning process. For example, the device selection in federated learning. Finally, we study the training performance of MNN on mobile GPUs. Since MNN's GPU support for training is not complete, we manually add support for several missing operators like one hot. As summarized in the figure below, both Mali and Andruno runs much slower than CPU. It varies between 1.8 and 12 times gap That is because, as we discussed before, MNN splits common operators into smaller, more basic operators. Many of those basic operators, like raster, are memory intensive, so cannot benefit from high parallelism of GPUs. Okay, that's all of our experiments. In this work, we perform first-of-its-kind measurements of on-device training performance on commodity smartphones. The results leads us to several interesting findings, emphasizing that we are at the dawn of learning everything and anytime. It calls for more research efforts in both theory and system aspects to enable such ubiquitous learning paradigm. Here, we highlight some of the promising future directions. First, generating efficient operators. While being the state-of-the-art training library for edge devices, our experiments show that MNN's performance is still far from optimal. One of the reasons is that the operators haven't been well-tuned. Second, memory optimization. As we have shown in the experiments, constrained by the physical RAM and the memory allocation strategies of OS, current mobile devices only allow a small batch size in training typical CNN models. Such a limitation may harm the convergence performance for both accuracy and overclock time. Therefore, memory optimization are needed to enable training on large enough batch size. Last one, tuning system parameters. Considering the hardware heterogeneity across devices and the dynamics of network bandwidth, it's non-trivial to choose appropriate system configuration for each device. Each system parameters like CPU cores and frequency open rich channels for on-device training performance. That is training time and energy consumption. For example, in federated learning, many devices equipped with a heterogeneous processor may leverage different CPU frequency to keep a synchronized pace while reducing the overall energy consumption. That's all. Thank you for listening.